In 1969, 12 human beings walked on the surface of the moon. The last of them left in December 1972. Since that day, no human has traveled beyond low Earth orbit. That is more than 50 years of silence, 50 years of footprints, undisturbed in the lunar dust, perfectly preserved in the airless vacuum of a world that has been waiting. NASA's Artemis program was supposed to change that. It was announced in 2017 with a bold promise: return humans to the moon, and this time, stay. Not just plant a flag, but build something lasting. The original plan called for boots on the lunar surface by 2024. That deadline passed without a launch. Then the window shifted to 2025. That passed too. Right now, as of early 2026, the Artemis II mission, which carries the first human crew to the vicinity of the moon since Apollo 17, is still sitting on a launch pad in Florida, delayed by technical problems that reveal something important about the enormous complexity of what we are trying to do. Understanding why this program keeps slipping behind schedule is not just a story about bureaucracy or bad luck. It is a story about the fundamental physics of deep space travel, the chemistry of cryogenic rocket fuel, the biology of human bodies in space, the engineering of systems that must work perfectly every single time, and a geopolitical race that is quietly reshaping the future of space exploration. Let us start at the beginning. The Space Launch System, commonly referred to as the SLS, is the most powerful rocket NASA has ever built. It stands 98 meters tall, roughly the height of a 32-story building, and at full thrust it generates 4 million kilograms of force. It burns a combination of liquid hydrogen and liquid oxygen, two of the most energetically efficient propellants available, but also among the most difficult to handle. Liquid hydrogen must be stored at negative 252 degrees Celsius. That is just 21 degrees above absolute zero, the coldest temperature theoretically possible in the universe. At that temperature, hydrogen becomes a cryogenic liquid, shrinking in volume by a factor of roughly 800 compared to its gaseous state. Keeping it liquid requires extraordinary insulation, and any gap in a seal, any imperfection in a valve, any microscopic pathway through a joint allows it to leak. When engineers conducted the first fueling test of the Artemis II mission in late January 2026, a procedure called a wet dress rehearsal, they loaded approximately 2.6 million liters of liquid hydrogen and liquid oxygen into the rocket stages and ran a simulated countdown. During the process, sensors detected a liquid hydrogen leak. This was not a catastrophic failure. Hydrogen leaks are a known risk in cryogenic rocketry, and the teams had contingency procedures ready. They replaced the affected seals and a ground support filter, then prepared for a second fueling test. The second rehearsal, completed on the 19th of February 2026, went considerably better. No leaks were detected. The tanks were filled to capacity. The countdown simulation completed successfully. Engineers signed off on the rocket as ready to proceed toward launch. Then, during a routine procedure to purge and repressurize the systems after the test, something unexpected happened in a section of the rocket called the interim cryogenic propulsion stage. This is the upper stage of the SLS, the component responsible for the final push that sends the Orion capsule out of low Earth orbit toward the moon. Engineers discovered that helium was not flowing correctly through the stage's internal plumbing. Helium plays a critical role in rockets like the SLS. It is used to maintain pressure inside the propellant tanks, preventing them from collapsing as the fuel is consumed. It is also used to purge the engine lines, flushing out residual propellants and preventing dangerous buildups. Without proper helium flow, the propulsion system cannot function safely. The source of the problem was traced to a faulty seal and a check valve. The fix required access to a section of the rocket that is completely inaccessible while the vehicle is standing on the launch pad. There was only one option: roll the entire stack back to the vehicle assembly building, disassemble the affected section, make the repairs, reassemble, and roll back out. The vehicle assembly building at Kennedy Space Center is one of the largest structures in the world by enclosed volume. Originally built for the Saturn V moon rockets of the Apollo program, it was later modified for the Space Shuttle and has now been adapted again for the SLS. Rolling the fully assembled rocket and spacecraft stack in and out of this building is not a trivial operation. The crawler transporter that carries the stack moves at a maximum speed of about 1 kilometer per hour. The entire rollback and rollout cycle takes days, adds costs, and further delays the launch window. This sequence of events, the hydrogen leak, the helium valve failure, the rollback, highlights something deeper about the challenge of modern spaceflight. The SLS is an extraordinarily complex machine. It contains millions of individual components, thousands of sensors, and systems operating simultaneously across a range of extreme temperatures and pressures. The more complex a system is, the more potential failure points it contains. That is not a flaw in the design. It is a mathematical consequence of trying to keep human beings alive in the most hostile environment the solar system has to offer. There is an additional factor that makes this complexity more dangerous: frequency. In the Apollo program, Saturn V rockets launched more than a dozen times over the course of roughly 4 years. That cadence of use meant that engineers and technicians were constantly working with the hardware. They developed what practitioners sometimes call muscle memory. At an institutional level, a deep familiarity with the systems that comes only from repeated hands-on experience. The SLS, by contrast, launched for the first time in November 2022 as part of the uncrewed Artemis I mission. That was the only time it has ever flown. Nearly 4 years passed between that launch and the current attempt to fly Artemis II. NASA Administrator Jared Isaacman has described the situation using the term skill atrophy, the gradual erosion of technical proficiency that occurs when a workforce does not regularly practice the procedures it is responsible for executing. When people go years between attempts at a complex technical task, errors become more likely. Small details are forgotten. Procedural knowledge fades. To address this, NASA has adopted a plan to increase the cadence of SLS launches to approximately 1 mission every 10 months. The logic is straightforward. More frequent launches keep both the hardware and the people who operate it in better working condition. Whether this goal is achievable in practice remains to be seen. First, Artemis II must actually get off the ground. Beyond the mechanical challenges of launching the rocket, there are deeper questions about the risks that human crew members will face during the mission. It has been more than 50 years since a crewed spacecraft traveled beyond low Earth orbit. The radiation environment beyond the protection of Earth's magnetic field is significantly more intense than what astronauts experience on the International Space Station. The communication delays, the thermal extremes, the isolation, all of these factors create compounded risks that do not exist in orbital spaceflight. The crew of Artemis II, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, will not land on the moon. Their mission is a 10-day lunar flyby, during which they will test the life support systems, navigation hardware, communications infrastructure, and emergency protocols of the Orion spacecraft in deep space conditions. This is a critical step. Before anyone attempts to land on the lunar surface, NASA needs to verify that every major system in the Orion capsule functions as expected when it matters most, with people inside, far from Earth. There is a sobering reality behind this mission plan that deserves to be stated plainly. The Orion capsule has flown exactly once during the uncrewed Artemis I mission. While that flight was broadly considered a success, it was not without problems. Post-flight inspection of the spacecraft revealed that the heat shield, a critical component responsible for protecting the capsule and its occupants during re-entry into Earth's atmosphere, had behaved in unexpected ways. The heat shield on Orion is covered with a material called avcoat, an ablative compound that was also used on the Apollo capsules. The term ablative refers to the way the material works. It absorbs heat by charring and eroding away, rather than simply conducting heat into the capsule structure. This process is highly effective, but it depends on the material behaving predictably under the intense thermal conditions of atmospheric re-entry. During Artemis I, Orion re-entered the atmosphere, traveling at approximately 40,000 kilometers per hour. The frictional heating at that speed is extreme temperatures on the shield surface reach thousands of degrees Celsius. Post-flight analysis found that the avcoat material had chipped and eroded in more than 100 locations in ways that had never been observed during the Apollo missions. Despite the fact that the same basic material was used, the investigation into why this happened revealed a subtle but critical mechanism. During re-entry, the intense heat causes gases to be generated within the ablative material as it breaks down. Normally, these gases escape outward through the charred outer layer of the shield. In the case of Orion's heat shield, engineers found that this gas permeation pathway was insufficiently open. The gases could not escape quickly enough, causing internal pressure to build up until the shield cracked and shed material. Under the specific thermal conditions of a crewed lunar return, this kind of failure could be catastrophic. NASA's response to this problem was pragmatic, though it carries its own trade-offs. Rather than redesign the heat shield entirely, a process that would take years and cost hundreds of millions of dollars. Engineers decided to change the way the Orion capsule re-enters the atmosphere. During Artemis I, Orion used a technique called a skip entry maneuver. In this approach, the capsule dips into the upper atmosphere at a shallow angle, decelerates, briefly exits the atmosphere again like a stone skipping across water, and then performs a final re-entry. This technique reduces the peak deceleration forces experienced by the crew and allows for more precise landing zone targeting. However, the analysis of the heat shield damage revealed that the skip entry profile actually made the internal gas pressure problem worse. The two-phase re-entry creates conditions that trap gases in the avcoat material more effectively than a direct re-entry would. For Artemis II, NASA will eliminate the skip phase and use a steeper, more direct re-entry trajectory. This approach is harder on the crew in terms of the deceleration forces they must endure, but it produces a more uniform thermal environment on the heat shield that allows gases to escape more readily. The astronauts will experience higher G-forces during landing, but the shield will behave more predictably. This change represents a deliberate choice to prioritize safety over crew comfort. This brings us to what is arguably the most significant change to the Artemis program in its history. For the first 9 years of the program's existence, the mission called Artemis III was planned as the Grand Return, the mission that would put human beings on the surface of the Moon for the first time since December 1972. Artemis III was to be the crescendo, the historic moment. As of February 2026, that plan no longer exists. Artemis III has been completely redefined. It will no longer attempt a lunar landing. Instead, it has been redesigned as a 30-day systems verification mission in low Earth orbit. The purpose of this redesigned mission is to test all of the hardware and procedures that would eventually be needed for a lunar landing, but in the relative safety of Earth's backyard, where rescue and contingency options exist that simply do not exist on the far side of the Moon. The reasons for this change are grounded in risk analysis. The original Artemis III plan was extraordinarily ambitious, asking multiple systems to perform critical functions for the first time, simultaneously, at a distance of nearly 390,000 kilometers from Earth. To understand why this was considered too risky, it helps to understand what the landing sequence actually requires. The plan was for the Orion capsule, carrying the astronauts, to travel to the Moon and enter lunar orbit. There, the crew would perform a docking maneuver with SpaceX's Starship Human Landing System, a massive vehicle that would transport the astronauts from lunar orbit to the surface and back. This docking would have been the first time Orion had ever docked with another spacecraft while in lunar orbit. The Starship vehicle itself requires more than a dozen separate tanker flights to refuel, before it can make the journey from Earth orbit to the Moon and back, a logistics chain that has never been attempted at this scale. The spacesuits planned for the surface excursions, known as the Axiom Extravehicular Mobility Unit, had never been tested in the actual vacuum of space, and the combination of cryogenic propellant transfer, deep space rendezvous, new suit performance, and lunar surface operations was all supposed to happen together for the first time with no backup plan closer than a 3-day trip back to Earth. An independent safety review panel described this constellation of factors as representing a compounded level of technical risk that was unjustifiable given what was known at the time. NASA agreed and restructured the mission accordingly. This restructuring draws a deliberate parallel to an earlier decision made during the Apollo program. In the spring of 1969, before the Apollo 11 lunar landing mission launched, NASA flew a mission called Apollo 9. That mission never left Earth orbit. Its purpose was to test the lunar module, the vehicle that would actually land on the Moon in conditions where an emergency abort could bring the crew home quickly. Only after Apollo 9 verified that the lunar module worked as designed did NASA proceed with the lunar landing missions. Artemis III is now serving a similar function, a controlled, lower-stakes environment in which to verify the hardware before committing to the high-stakes mission. Specifically, the redesigned Artemis III will see the Orion capsule rendezvous and dock with either SpaceX's Starship or Blue Origin's Blue Moon lander system in low Earth orbit. The crew will test life support systems, inter-vehicle docking procedures, communications between vehicles, and emergency protocols, all in an environment where, if something goes wrong, they can return to Earth in hours rather than days. This change in mission architecture has been accompanied by another significant engineering decision involving the rocket itself. For years, the planned evolution of the Space Launch System included an upgraded version called the Block 1B configuration. The key feature of Block 1B was a new upper stage called the Exploration Upper Stage, which would replace the current Interim Cryogenic Propulsion Stage. The Exploration Upper Stage was designed to be significantly more powerful, enabling heavier payloads to be sent toward the Moon. But this stage experienced years of development delays and substantial cost overruns. Under the current NASA leadership, the Exploration Upper Stage has been canceled entirely, along with the broader Block 1B and Block 2 upgrade path. In its place, NASA has selected a different upper stage, the Centaur 5, produced by United Launch Alliance. The Centaur 5 is a dual-engine stage that is already in service on United Launch Alliance's Vulcan rocket, meaning it carries a proven track record rather than requiring development from scratch. In terms of propellant capacity, it holds approximately twice as much fuel as the current Interim Cryogenic Propulsion Stage. Critically, it is compatible with the existing mobile launcher infrastructure at Kennedy Space Center, which means that adopting this stage does not require the construction of an entirely new launch tower and ground support system. The standardization around this configuration is a central part of NASA's strategy to achieve the goal of launching roughly once every 10 months. So when will human beings actually land on the Moon? The current target for Artemis IV, the mission that has now inherited the responsibility of being the first crewed lunar landing, is early 2028. That timeline is contingent on Artemis II and Artemis III proceeding without major new problems, on the Centaur 5 upper stage integration proceeding as planned, and on the various landing system elements being ready in time. The target landing site for Artemis IV is the south pole of the Moon, and this choice is not arbitrary. It represents one of the most scientifically and strategically significant destinations in the inner solar system. The Moon's rotational axis is nearly perfectly vertical tilted, only about 1.5 degrees relative to its orbital plane. For comparison, Earth's axis is tilted about 23.5 degrees, which is why we experience seasons. The Moon's negligible axial tilt means that sunlight always strikes its surface from a very low angle near the poles. In the floors of deep polar craters, sunlight never reaches at all. These regions are called permanently shadowed regions, and temperatures inside them can drop to approximately -240 degrees Celsius. That is colder than the surface of Pluto, colder than any surface temperature recorded anywhere in the inner solar system. These extraordinary conditions have a remarkable consequence. Because the temperatures are so low, volatile molecules that reach these craters delivered by comets and asteroids over billions of years cannot escape. Water molecules that drift into these shadowed craters freeze solid and accumulate over geological timescales. Scientists have confirmed the presence of water ice in these permanently shadowed regions through multiple orbital instruments, including the Lunar Crater Observation and Sensing Satellite mission, which deliberately impacted a South Pole crater in 2009 and detected water vapor in the debris plume. The importance of this ice for future exploration cannot be overstated. Water can be broken down through electrolysis into hydrogen and oxygen, the components of rocket propellant. A future facility capable of harvesting lunar ice and converting it into fuel could transform the Moon into a logistics hub for deep space exploration. Any mission heading toward Mars or the outer solar system could potentially stop at a lunar fuel depot, dramatically reducing the amount of propellant that needs to be launched from Earth's deep gravity well. This concept is sometimes described as using the Moon as a gas station for the solar system. One specific location of intense interest is Shackleton Crater, located almost exactly at the lunar South Pole. It is 21 kilometers wide and 4 kilometers deep. The crater walls are steep enough in places to exceed a 30-degree slope. Because of its depth and geometry, its interior remains permanently shadowed, while nearby crater rims receive near-constant sunlight, making them ideal locations for solar power generation. This combination of accessible solar energy and adjacent ice deposits makes Shackleton and its surroundings potentially the most valuable real estate in the solar system beyond Earth. Artemis IV will carry an array of scientific instruments designed to characterize this environment. One of the most significant is DUSTER, the Dust and Plasma Environment Surveyor, which will ride on a small autonomous rover called MAP. Lunar dust is one of the most persistent engineering challenges in moon exploration. Unlike terrestrial dust, which is rounded by weathering and water, lunar regolith consists of tiny, angular fragments of volcanic glass that have been shattered by billions of years of micrometeorite bombardment. These particles are electrostatically charged by the solar wind, causing them to cling aggressively to surfaces. They infiltrate seals, degrade optical systems, and if inhaled, can cause serious respiratory damage. Understanding exactly how dust behaves near a lander engine plume or in the footsteps of walking astronauts is critical to designing equipment that can survive and operate on the lunar surface for extended periods. The South Pole Seismic Station, which will also be deployed during Artemis IV, will listen for moonquakes and meteorite impacts, building on the seismic monitoring work done during the Apollo missions. During Apollo, the seismometers placed on the moon operated for years and revealed that the moon is seismically active in ways scientists had not anticipated. Artemis IV will extend this record with modern instrumentation and will add a new technique, a device called a thumper, which creates controlled seismic pulses at the surface. By analyzing how these waves travel through the subsurface, scientists can create a profile of what lies beneath the landing site, including the potential detection of buried ice deposits. The astronauts who walk on the lunar South Pole will wear a new generation of spacesuit called the Axiom Extravehicular Mobility Unit, developed in partnership between NASA and the commercial company Axiom Space. The design process also involved the Italian fashion house Prada, which contributed expertise in materials science and structural design. This may seem like an unusual pairing, but Prada's involvement is focused on the performance properties of the suit materials, not their aesthetic qualities. The durability, flexibility, and thermal performance of specialized fabric systems are areas where high-end materials engineering has genuine technical relevance. The Apollo-era spacesuits, known as the A7L configuration, were remarkable achievements for their time, but they were also notoriously restrictive. The pressurized suit created a stiff shell around the astronaut's body that made certain movements extremely difficult. Astronauts on the lunar surface often moved in what was described as a bunny hop, a two-footed jumping stride, because the suit's stiffness made it difficult to bend the knees and walk normally. The Axiom Extravehicular Mobility Unit uses a hybrid architecture combining hard shell, structural components with advanced flexible fabric joints, providing a range of motion that would have been impossible in the earlier design. The suit incorporates a life support system capable of maintaining stable conditions inside the suit for at least 2 hours in the extreme cold of the permanently shadowed regions. It includes a communication system developed with Nokia that uses 4G and LTE protocols for data transmission, and a visor system developed with Oakley, designed to manage the challenging optical conditions at the poles where sunlight always comes from very low angles. The suit's seals and materials have been specifically engineered to resist infiltration by lunar dust, a critical improvement over the Apollo suits, which showed evidence of dust-penetrating joint systems even during the relatively brief surface excursions of the 1960s and 70s. Artemis III will be the first time these suits are deployed in the actual vacuum of space, providing real-world performance data before they are relied upon for the lunar landing in 2028. There is one more dimension of the Artemis program that matters deeply to the people who design it and fund it, and that is geopolitical. The return to the moon is not happening in isolation. It is happening in the context of a new era of competition in space, one that shares some characteristics with the original space race of the 1950s and 60s, but differs in important ways. The People's Republic of China has been executing a systematic and methodical program of lunar exploration for more than a decade. Chinese missions have landed on the far side of the moon, a first in history, and returned samples from the lunar surface. China has announced plans for a crewed lunar landing by approximately 2030, and is developing the launch vehicles and spacecraft to make this happen. Chinese officials have also described plans for a permanent research station at the lunar South Pole, to be developed in cooperation with other nations under a framework called the International Lunar Research Station. American officials and space policy analysts have raised concerns about what some describe as space sector capture, the possibility that China could establish a physical presence at the South Pole's resource-rich locations and, through the logic of prior presence and practical control, effectively limit access by other actors. The South Pole ice deposits that make the region scientifically valuable also make it strategically valuable. Control over the water ice at the poles could mean control over the most important source of space-based rocket propellant in the near solar system. For any nation hoping to sustain a long-term human presence beyond Earth, access to those resources could be decisive. This is the context in which the Artemis timeline pressure exists. It is not simply that NASA wants to demonstrate technical capability. There is a genuine strategic dimension to the race to establish a permanent presence at the South Pole, and the slipping timelines of the Artemis program create real anxiety among American space policy planners about whether the United States will arrive first or second at the most important destination in the solar system. The fundamental difference between this era of space competition and the original space race is the nature of the goal. In the 1960s, the objective was symbolic. Be first, plant the flag, demonstrate national prestige. The Apollo program accomplished that goal. 12 people walked on the moon, and then the program ended because the symbolic objective had been achieved. The objective now is not symbolic. It is economic and infrastructural. The nation, or coalition of nations, that establishes the first sustainable, operational presence at the lunar South Pole will have a profound advantage in the next phase of solar system exploration. This is not about flags. It is about who controls the fuel. This shift in motivation requires a different kind of program. Not a sprint, but a sustained effort to build the logistics, the infrastructure, the technical knowledge, and the international partnerships that a permanent presence requires. The Artemis program, for all its delays and technical challenges, is attempting to build something that Apollo never tried to build: a foundation. The transition from the original exploration upper stage to the Centaur 5 standardizes the rocket configuration across multiple missions and makes the 10-month launch cadence target more achievable. The redesignation of Artemis III as a systems verification mission in low Earth orbit reduces the risk of a catastrophic early failure that could terminate the entire program. The choice of the lunar South Pole as the landing target connects the human exploration mission directly to the resource extraction and propellant production capabilities that a self-sustaining presence requires. Taken together, these decisions reflect a program that has learned from its delays and reconfigured itself to be more durable, if slower, than the original plan envisioned. What remains deeply uncertain is the timeline. The target of early 2028 for the first crewed lunar landing assumes that Artemis II flies successfully, that the redesigned Artemis III mission accomplishes its verification objectives without major new problems, that the Centaur V integration proceeds as planned, and that the SpaceX Starship, or Blue Origin Blue Moon lander, is ready in time. Any one of these dependencies encountering serious technical problems could push the landing further into the future. There are also ongoing questions about the heat shield. While the decision to abandon the skip entry maneuver for Artemis II addresses the immediate gas pressure problem, it does not definitively resolve the question of how the Avcoat material will behave under all conceivable re-entry conditions. The change to a direct re-entry trajectory is based on analysis and modeling, but models are only as good as the assumptions that go into them. The actual behavior of the system in flight will provide new data that either confirms the analysis or reveals new complications. Questions about the long-term human health effects of extended exposure to deep space radiation also remain active areas of research. Beyond Earth's magnetic field, astronauts are exposed to galactic cosmic rays, high-energy particles originating from outside the solar system, as well as solar energetic particles produced by eruptions on the Sunday. The cumulative radiation dose received during a multi-week lunar mission is significantly higher than what International Space Station crew members receive over the same period. For missions involving long surface stays, this exposure becomes one of the primary health risks to manage. Water ice, if present in sufficient quantities at the South Pole, could actually help address this problem. Water is an effective radiation shield, and a habitat partially or fully buried under a layer of regolith mixed with water ice could provide meaningful protection against both galactic, cosmic rays, and solar particle events. Understanding the actual distribution and accessibility of the ice, not just its presence, is therefore important not only for propellant production, but for habitat design. The seismic data from the South Pole Seismic Station will contribute to understanding the subsurface structure beneath the landing site, which is also critical for evaluating whether underground construction is practical. On Earth, underground facilities are standard for applications requiring radiation shielding, pressure containment, or temperature stability. On the Moon, the same principles apply, but the engineering challenges are compounded by the nature of the regolith, the absence of water as a construction material, and the extreme temperature gradients between illuminated and shadowed surfaces. Much of this lies in the future. The immediate task is simpler in concept, though enormously difficult in practice. Get a rocket off the ground, send 4 people around the Moon, and bring them home safely. NASA has done this before. The Apollo program demonstrated that it is physically possible. What has changed is the complexity of the systems, the length of time since the last attempt, and the ambition of what comes next. The road from where the program stands today, a rocket on a launchpad in Florida, awaiting its first crewed mission since the Apollo era, to a permanent human presence at the lunar South Pole, is long and technically demanding. Every delay, every leak, every valve failure, every redesigned mission architecture is part of the process of building the knowledge and infrastructure that a durable presence requires. None of these setbacks are signs that the goal is unachievable. They are signs that the goal is genuinely difficult, and that the people working toward it are taking its difficulty seriously. What scientists and engineers still need to learn is substantial. They need real-world data on how the Orion capsule and its heat shield perform with crew on board. They need to understand exactly how and where water ice is distributed beneath the surface of the South Pole craters. They need to know how lunar dust behaves in the vicinity of operating spacecraft and suited astronauts, and how quickly it damages the seals and joints of surface equipment. They need to verify that cryogenic propellant can be transferred from one spacecraft to another in the operational conditions of deep space. And they need to demonstrate that the complex supply chain required to sustain a permanent lunar presence, including the fuel production, the communications relay infrastructure, and the surface mobility systems, can be operated reliably and cost-effectively. Each Artemis mission is designed to answer some of these questions and generate new ones. The transition from Artemis II to Artemis III to Artemis IV represents a logical progression from life support and navigation verification to docking and suit verification to landing and surface operations. The goal is a sustainable program, one that does not depend on any single perfect mission, but builds capability and knowledge incrementally. The Moon's South Pole is a destination unlike any previously explored in human history. It combines extreme physical conditions with extraordinary scientific potential and profound strategic importance. The permanently shadowed craters preserve a record of the early solar system, including the composition of the impactors that shaped both the Moon and the early Earth. The ice deposits represent the most accessible source of space-based water in the inner solar system. And the polar geometry, with its combination of permanent shadow and near-permanent sunlight on elevated ridges, creates conditions uniquely suited to a permanent human base. The path to that destination in 2028, if the timeline holds, runs directly through the rocket currently sitting on launchpad 39B at Kennedy Space Center. The hydrogen valves have been replaced. The helium check valve has been repaired. The crew is in pre-launch quarantine. The countdown is waiting. Whether or not the launch holds to its current schedule, the destination remains the same. The south pole of the Moon, with its ancient ice and its billion-year shadows, is waiting in the same silence as those Apollo footprints. The question is not whether humanity will return. The question is when, and who will be there when it matters most. To fully understand what makes this moment in space history so consequential, it helps to trace the arc of what was lost and what was gained in the 50 years between Apollo and Artemis. The Apollo program was, in many respects, the result of a specific historical accident, a geopolitical rivalry so intense that two superpowers were willing to spend what would be hundreds of billions of dollars in today's money to be the first to put footprints on the Moon. The scientific rationale for going to the Moon existed and was genuine, but it was not the primary driver. The primary driver was the Cold War. When President John F. Kennedy stood before Congress in May 1961 and declared that the United States would land a man on the Moon before the end of the decade, NASA did not yet have the technology to accomplish this. The agency had put one American in space, Alan Shepard, just 3 weeks earlier, on a 15-minute suborbital flight that barely crossed the boundary of space before coming back down. The Soviet Union, meanwhile, had already demonstrated orbital spaceflight with Yuri Gagarin's mission in April 1961. The United States was behind, visibly and embarrassingly behind, in what was framed as a critical demonstration of technological and ideological supremacy. The decision to race to the Moon was, in retrospect, an extraordinary gamble. At the time Kennedy made his declaration, NASA did not know what kind of trajectory the lunar mission would use, what the spacecraft would look like, how the landing would be executed, or whether it was even possible to return from the lunar surface reliably. These questions were answered, one by one, through a series of missions, Mercury, Gemini, and then Apollo, that proceeded at a pace that would be considered reckless by modern risk management standards. The Gemini program, which flew from 1964 to 1966, conducted 10 crewed missions in roughly 22 months. The primary purpose of Gemini was to develop the techniques that Apollo would require: spacewalks, orbital rendezvous and docking, extended duration missions, and precision re-entry. The pace of learning was astonishing, and the cost in human terms was also significant. 3 Apollo astronauts, Gus Grissom, Ed White, and Roger Chaffee, died in January 1967 when a fire broke out inside the Apollo 1 capsule during a ground test. The program paused, investigated, and redesigned critical systems before flying again. When Apollo 11 finally lifted off from Kennedy Space Center on the 16th of July, 1969, it was carrying technology that was, by the standards of the day, at the absolute frontier of what was achievable. The guidance computer aboard the spacecraft had less processing power than a modern pocket calculator. The astronauts navigated partly by looking at stars through a sextant and performing manual calculations. The lunar module that carried Neil Armstrong and Buzz Aldrin to the surface had walls so thin, approximately the thickness of 2 layers of aluminum foil, in some places that puncturing it with a dropped tool was a genuine concern, and yet it worked. On the 20th of July, 1969, Armstrong stepped onto the lunar surface and uttered what became perhaps the most famous statement in the history of exploration. Over the following 3.5 years, 11 more astronauts walked on the moon across 5 subsequent missions. The last humans to stand on the lunar surface were Eugene Cernan and Harrison Schmitt during the Apollo 17 mission, which concluded on December 14, 1972. Cernan was the last person to walk on the moon, and his final act before climbing back into the lunar module was to trace his initials in the dust. Then the program ended. The remaining 3 Saturn V rockets that had been built for Apollo missions that were canceled, Apollo 18, 19, and 20, were put on display in museums. The workforce dispersed. The contractors moved on to other projects. The institutional knowledge accumulated through 10 years of intensive development and 12 crewed lunar missions did not transfer cleanly into any successor program. It dissipated. When NASA eventually tried to build new deep space capabilities decades later, engineers found themselves rediscovering solutions to problems that had been solved in the 1960s but never adequately documented. This is part of why the SLS development program, which began in earnest around 2011, took far longer than initially projected and cost far more than the original estimates suggested. The Saturn V had been a remarkable machine, but it was a product of specific industrial circumstances, a vast, wartime-like mobilization of American engineering talent funded by Cold War urgency. Recreating those capabilities in a different institutional and budgetary environment proved profoundly difficult. The SLS shares several characteristics with the Saturn V. Both use a combination of solid rocket boosters and liquid-fueled core stages. Both burn cryogenic propellants. Both are designed to place large payloads on translunar trajectories. But the SLS uses different engines, different materials, different manufacturing techniques, and different software than the Saturn V, and the organization that built it is structurally different from the NASA of the 1960s. The program was managed by the same traditional large aerospace contractors, Boeing, Northrop Grumman, Aerojet Rocketdyne, that had been involved in NASA contracting for decades, under cost-plus contracting arrangements that critics argued did not provide sufficient incentive for cost and schedule performance. The result was a rocket that took approximately 11 years from formal program start to first flight at a total development cost of more than $23 billion. Each SLS launch is currently estimated to cost between $2 billion and $4 billion, depending on what costs are included in the calculation. These numbers have attracted sustained criticism, particularly in comparison to the cost trajectory of commercial launch providers such as SpaceX, whose Falcon Heavy rocket can place a comparable payload into low Earth orbit at a small fraction of the cost. The involvement of SpaceX in the Artemis program, specifically as the provider of the Starship human landing system that will carry astronauts from lunar orbit to the surface, represents a deliberate attempt by NASA to leverage the cost reductions that commercial development has achieved. SpaceX won the Human Landing System contract in April 2021, defeating competing proposals from Blue Origin and a consortium led by Dynetics. The decision to award the contract to a single provider rather than maintaining competition was controversial, and Blue Origin filed a legal challenge that delayed the program by several months before being dismissed. Starship is a fundamentally different kind of spacecraft than anything that has flown before. It is designed to be fully reusable. Both the Super Heavy booster that launches it from Earth and the Starship upper stage itself are intended to land and fly again. In its maximum configuration, Starship is approximately 120 meters tall and is designed to carry payloads of more than 100 metric tons to low Earth orbit. For comparison, the SLS Block 1 rocket can carry approximately 95 metric tons to low Earth orbit, and it is not reusable. The cost difference between a reusable and expendable rocket of equivalent capability is potentially enormous in the long run, though fully realizing the potential requires the reusability systems to actually work reliably. Starship's development has proceeded rapidly by historical standards, but it has also encountered substantial technical challenges. The vehicle requires a complex heat shield consisting of thousands of individually installed ceramic tiles, similar in concept to those used on the space shuttle, but implemented differently. It requires an unprecedented orbital propellant transfer capability, the ability to transfer cryogenic liquid methane and liquid oxygen between spacecraft in orbit, while both vehicles are in microgravity. And the version designed for lunar landing must be specifically adapted for the vacuum environment and low gravity of the Moon, with a different propulsion configuration than the Earth launch version. None of these capabilities have been demonstrated in flight at the time of this writing. The path from the current state of Starship development to a vehicle capable of accepting a transfer of crew from an Orion capsule in lunar orbit, landing at the South Pole, and returning the crew to lunar orbit for rendezvous, is a path that requires multiple additional test milestones to be successfully completed. Blue Origin, the aerospace company founded by Amazon founder Jeff Bezos, is also developing a lunar lander called Blue Moon. While Blue Origin was not selected for the initial human landing system contract, the company continued development of Blue Moon, and NASA has awarded a contract to Blue Origin under the broader Sustainable Lander program. The redesigned Artemis III mission, the Low Earth Orbit Systems Verification flight, will rendezvous with either Starship or Blue Moon, depending on which vehicle is ready in time, allowing both programs to contribute to the verification mission. The relationship between NASA's government-developed hardware and the commercial providers raises questions that will continue to be debated throughout the program's life. The SLS and Orion represent the government-owned, government-operated core of the system. They are expensive per flight, but have the advantage of being entirely within NASA's programmatic control. The commercial human landing system, whether Starship or Blue Moon, offers the potential for dramatically lower costs in the long run, but introduces dependencies on corporate development timelines and technical progress that NASA cannot directly control. What NASA is attempting to build is a hybrid architecture, a government core that provides the reliable, proven foundation for the mission, connected to commercial systems that provide the more specialized capabilities required for surface access and eventually for resource utilization. Whether this hybrid approach produces a sustainable program at acceptable cost remains to be demonstrated. The international dimension of Artemis is also significant. Unlike Apollo, which was fundamentally a bilateral race between two nations, Artemis is being conducted under a framework called the Artemis Accords, a set of principles for responsible behavior in space exploration that have been signed by more than 40 countries as of 2026. The Accords address topics including transparency of operations, interoperability of systems, the release of scientific data, and the handling of historic heritage sites on the Moon, including the Apollo landing sites. The Artemis Accords are not a treaty in the formal legal sense. They do not require ratification by national legislatures and have no enforcement mechanism. But they represent an attempt to build a community of like-minded nations around shared norms for space exploration, and the list of signatory nations has grown substantially since the Accords were first introduced in 2020. Canada contributed an astronaut, Jeremy Hansen, to the Artemis II crew, reflecting its participation in the program through the Canadian Space Agency's contribution to the Lunar Gateway project. The Lunar Gateway is a planned small space station in lunar orbit that is intended to serve as a staging point for surface missions. It is being developed as an international project, with contributions from Canada, Japan, the European Space Agency, and other partners. The Gateway is not essential for the initial Artemis landing missions, which are designed to operate without it, but it is central to the long-term concept of a sustainable lunar presence. A permanent outpost in lunar orbit provides a location for long-duration crewed missions near the Moon without the full logistical requirements of a surface base, a location for scientific research that benefits from the lunar environment without requiring surface landings, and a jumping-off point for surface operations that can be conducted incrementally as capabilities develop. Russia, which was a core partner in the International Space Station program for decades, is not participating in Artemis. Following geopolitical developments in 2022, Russia announced that it would withdraw from International Space Station operations after 2024 and pursue its own lunar exploration program in partnership with China. This marks a significant restructuring of the international landscape of space exploration, effectively creating two separate programs with overlapping but distinct goals and landing sites. The competition for the south pole of the moon now involves at least four major players: the United States and its Artemis Accords partners, China and its International Lunar Research Station partners, which include Russia, private commercial entities operating independently, and potentially other national space programs that have not yet committed to a particular alignment. The South Pole's limited number of ideal landing sites, areas that combine proximity to ice deposits with access to sunlight for power generation, means that the question of who is where first is not merely symbolic. First arrivals establish infrastructure, and infrastructure creates dependencies that are difficult to undo. The physics of the moon's poles reinforces this strategic reality. The near constant sunlight available on certain elevated ridges and crater rims near the poles is a finite resource. The landing pads, solar arrays, communication systems, and surface mobility infrastructure needed to access the ice deposits in the permanently shadowed craters below those ridges take up physical space. The best spots are limited. This is why NASA planners and policy analysts have been increasingly vocal about the importance of establishing a presence at the South Pole on a timeline that does not cede the most advantageous locations to other actors. Understanding the distribution of ice within the permanently shadowed regions is itself a major scientific objective of Artemis IV and the missions that will follow. Orbital measurements have confirmed the presence of water ice, but have limited ability to characterize the ice in 3 dimensions. Ground truth measurements from surface instruments and drilling operations are essential for determining whether the ice is a thin frost spread across the crater floor, a deeper deposit of mixed ice and regolith, or in some locations, a relatively pure ice body that could be mined efficiently. The answer to this question has enormous practical implications. A thin frost, distributed over a large area, is difficult to harvest efficiently. A concentrated deposit of ice-rich regolith, even if not pure ice, could potentially be processed by a relatively simple heating and collection system. And if pure ice exists in certain locations, the economics of in-situ resource utilization could become compelling even in the near term. The concept of in-situ resource utilization, using local materials to produce the consumables needed for exploration rather than bringing everything from Earth, is central to every long-term plan for human presence beyond Earth. It is often abbreviated as ISRU, and it represents a fundamental shift in the economics of space exploration. Every kilogram of water, oxygen, or hydrogen that can be produced on the Moon or Mars is a kilogram that does not have to be launched from Earth at an enormous propellant cost. For a round trip from Earth to Mars, carrying all the necessary propellant from Earth multiplies the mass that must be launched from Earth's surface by a large factor. If even a fraction of the propellant can be produced at Mars, or at a lunar staging point, the required launch mass from Earth drops dramatically. This is why the water ice at the lunar South Pole is not primarily a scientific curiosity. It is a potential industrial feedstock for the entire future of human space exploration. The missions that characterize it, develop the technology to extract it, and demonstrate the production of propellant from it will determine whether human exploration beyond the Earth-Moon system is economically practical on a generational timescale. Artemis is, in this sense, not primarily a program to revisit the Moon. It is a program to determine whether the Moon can serve as the foundation for the next era of exploration. The technology required for this transition spans many disciplines. Robotic mining and excavation systems must be developed that can operate in the cold, vacuum environment of the permanently shadowed craters. Electrolysis systems capable of operating at small scale with lunar power budgets must be designed and tested. Cryogenic storage systems for the produced propellants must be adapted for long-term, uncrewed operation on the lunar surface. And all of these systems must be demonstrated to work reliably before anyone commits the resources to scaling them up. Several commercial and government missions are attempting to contribute to this understanding, even before the crewed Artemis landings. NASA's Commercial Lunar Payload Services program has contracted with multiple companies to deliver scientific and technology demonstration payloads to the lunar surface. Some of these have already flown. With mixed results, some missions succeeded and some encountered landing failures, highlighting that reaching the lunar surface reliably is still far from routine even for robotic missions. But each mission, successful or not, adds to the technical knowledge base. The relationship between robotic precursor missions and crewed exploration is one of the central strategic questions of the current era. The Apollo program relied heavily on robotic precursors. The Ranger, Surveyor, and Lunar Orbiter programs provided the surface imagery, geological characterization, and engineering data that made the Apollo landing sites selectable and the missions executable. For the Artemis South Pole landings, the need for precursor data is equally pressing. The terrain of the South Pole is far more complex than the relatively flat equatorial regions visited during Apollo, and the permanently shadowed regions have never been visited by anything at all. Landing a spacecraft at the South Pole requires navigating by radar and sensors in terrain that orbital imagery cannot fully characterize. In some cases, in complete darkness, where solar power is unavailable, and in extreme cold that challenges the electronics and mechanisms of the lander. The engineering solutions to these challenges, autonomous navigation systems, thermal management technologies, radiation-hardened electronics, capable of operating at very low temperatures, are being developed and tested through the Robotic Precursor Program. They are also being developed commercially by the various companies competing for lunar services contracts, driven by the expectation that a market for lunar services will exist in the coming decades. The maturation of this commercial ecosystem is perhaps the most structurally important development in space exploration since the development of the reusable launch vehicle. When SpaceX demonstrated that a commercial company could develop launch vehicles at dramatically lower costs than the traditional government contracting model, it changed the economics of access to low Earth orbit profoundly. If a similar dynamic plays out in lunar surface access, resource utilization, and ultimately transportation between Earth orbit and the Moon, the cost of operating in the cislunar environment could fall far enough to enable activities that are currently not economically viable. This includes not just scientific and government exploration, but eventually commercial activities, mining and resource extraction, manufacturing in the low-gravity environment, tourism, and the provision of services to crewed missions. None of these activities are imminent, and predicting when they become economically viable requires assumptions about technology development rates and market formation that carry enormous uncertainty. But the trajectory is visible, and the foundational technology development that makes these futures possible is happening now. For the 4 astronauts aboard Artemis II, none of these long-term economic and strategic considerations are the immediate concern. Their concern is executing a 10-day mission to the vicinity of the Moon and returning safely. They will fly the first crewed SLS and Orion mission in history. They will travel farther from Earth than any human being has traveled since the crew of Apollo 17 returned in December 1972. They will test the systems that future astronauts will rely on, gather the data that engineers need to certify the vehicle for the lunar landing missions, and demonstrate that the United States retains the capability to send human beings to the deep space environment. If everything goes as planned, the historic nature of the moment should not be understated. A gap of more than 50 years in human deep space exploration is about to end. The specific technical problems that have delayed the mission, the hydrogen leaks, the helium valve, the rollback and repair, are details in the larger story. They're the kinds of problems that arise whenever humans attempt something genuinely difficult, with technology operating at the frontier of what is possible. They are, in a certain sense, evidence that the mission is real, and the difficulty is real, and the stakes are real. The Moon is not going anywhere. The ice in the permanently shadowed craters has been accumulating for billions of years. It will still be there in 2028, or 2030, or whenever the first human beings actually descend to the South Pole. But the geopolitical and commercial dynamics that determine who gets there first and what infrastructure they build when they arrive are evolving on a faster timescale. The urgency is real, and the delays are costly, not just in budget and schedule, but in the strategic positioning that determines the long-term future of human activity beyond Earth. What makes this moment genuinely important in the history of exploration is not the drama of rockets on launch pads or the spectacle of re-entry firewalls. It is the quiet shift in the underlying purpose of the mission. Apollo was about proving something. Proving that human beings could leave the Earth and reach another world. That proof was provided. Artemis is about building something. A sustained, economically viable, internationally collaborative human presence beyond the Earth that does not depend on Cold War urgency to survive. Whether that is harder or easier than what Apollo accomplished is debatable, but it is different in kind, and the consequences of succeeding or failing to build it are different in kind as well. The current delays are not the end of the story. They are a chapter in a story that has been running for 60 years and will continue for centuries. The footprints that Cernan left on the Moon in December 1972 will remain undisturbed until a new set of boots walks past them. The question of when that happens, and what those astronauts find when they get there, and what they build when they stay, is one of the genuinely open questions of our time. Every science and engineering discipline involved in Artemis propulsion, materials science, cryogenics, radiation, biology, seismology, geochemistry, robotics, communications, life support is pushing against the boundaries of what is currently known and possible. The answers that come back from the lunar South Pole will not just tell us about the moon. They will tell us about the early history of the solar system, preserved in ice and rock that has not changed since the first billion years after the planets formed. They will tell us whether the resources needed to sustain human exploration beyond Earth actually exist in accessible form. And they will tell us whether human beings have the institutional endurance to pursue a goal across multiple decades, multiple administrations, multiple budget cycles, and multiple technical crises without abandoning it. That last question is perhaps the most important of all. The technology is advancing, the science is compelling, the strategic necessity is clear. What remains to be demonstrated is whether the commitment is durable. The rocket on the launch pad in Florida is a proxy for that question. When it finally rises and carries 4 human beings toward the moon, it will be an answer of a kind. And when, if the current plan holds, astronauts descend to the permanently shadowed crater floors of the lunar South Pole and begin the work of understanding and eventually utilizing what is there, that will be an answer of a more enduring kind. The foundation for the next century of human exploration is being laid right now, one valve repair at a time. To truly appreciate the scientific depth of what the Artemis missions are setting out to accomplish, it is worth examining the moon itself as a scientific object, not simply as a destination, but as a record of the early solar system that simply does not exist anywhere else in the inner solar system in comparable form. The moon formed approximately 4.5 billion years ago, within roughly 100 million years of the formation of the solar system itself. The most widely accepted theory for its formation, known as the giant impact hypothesis, proposes that a Mars-sized protoplanet, sometimes called Theia, collided with the early Earth in a glancing blow. The collision was catastrophic in scale. Both the Earth and the impactor were largely vaporized and melted, and the debris from the collision was thrown into orbit around what remained of the Earth. Over millions of years, this debris accreted under its own gravity into the moon. This origin story has several important scientific implications. The moon is composed largely of material from the outer layers of the early Earth. The same silicate rock and minerals that make up Earth's mantle mixed with material from the impactor. This is why the moon has a composition broadly similar to Earth's mantle, but is depleted in volatile elements, those that evaporate easily at high temperatures compared to Earth. The violence of the formation event drove off most of the moon's original water and other volatiles. This is precisely why the discovery of water ice at the poles was so surprising and scientifically interesting. If the moon lost its original water during formation, where did the polar ice come from? The answer, as best as scientists currently understand, is that it arrived later delivered by comets and water-bearing asteroids that impacted the moon over its long history. Some of this water was broken down by solar radiation or escaped to space, but some fraction, particularly water delivered to the polar regions where permanently shadowed craters act as cold traps, survived and accumulated. The ice that Artemis IV astronauts hope to sample may have been sitting in those craters for hundreds of millions, or even billions of years, preserved at temperatures barely above absolute zero. The scientific value of this ice is layered. Its chemical composition, specifically the ratios of different isotopes of hydrogen, hydrogen-1, deuterium, and possibly tritium and oxygen, can provide information about the origin of the water. Different sources of water in the early solar system had characteristic isotopic signatures. By measuring the isotopic composition of the lunar polar ice, scientists can potentially determine whether the water came primarily from comets, from carbonaceous asteroids, or from some other source. This is directly relevant to understanding where Earth's oceans came from, a question that remains actively debated. The polar ice may also contain other volatile materials: carbon dioxide, methane, ammonia, and more exotic molecules that arrived with the water-bearing impactors. These compounds are preserved in the cold trap environment, just as water is. Analyzing them provides a chemical snapshot of the early inner solar system that cannot be obtained from any other accessible location. Earth's geological activity has long since erased, or modified, most of the record of the first billion years of solar system history. The moon, geologically quiet for billions of years, has preserved it. The surface of the moon outside the polar craters also tells a story, though a different one. The vast, relatively flat dark plains that are visible from Earth with the naked eye are called the lunar maria, from the Latin word for seas, though they contain no water. They were formed between about 3 and 4 billion years ago, when large impact basins were flooded by volcanic lava flows. The lava solidified and is now exposed rock. By measuring the ages of samples from these surfaces through techniques such as radiometric dating, which uses the known decay rates of radioactive isotopes, scientists can construct a timeline of volcanic activity on the Moon and correlate it with events in the broader history of the solar system. The higher, lighter colored regions of the Moon are called the lunar highlands. They are older than the Maria, dating back to the very early history of the Moon shortly after formation. They are more heavily cratered because they have been exposed to impactors for longer. The rock of the highlands, called a northocite, is a mineral that forms when a magma ocean. The Moon is thought to have been largely or entirely molten. Shortly after formation cools, and certain minerals float to the top. Studying a northocite from the highlands tells scientists about the conditions in the earliest phase of the Moon's history. The Apollo missions returned 382 kilograms of lunar rocks and soil samples, which have been studied by laboratories around the world for more than 50 years and continue to yield new discoveries as analytical techniques improve. The samples have provided detailed chronologies of lunar volcanic and impact history, measurements of the abundance of solar wind particles that have been implanted in the lunar soil over billions of years, evidence for the early history of the Sun's magnetic field and particle output, and constraints on the age of the Moon that link it to the formation of the solar system. Artemis IV will land in a region that was never visited during Apollo, the South Polar region. The geological context of the South Pole is fundamentally different from the equatorial regions sampled by Apollo. The terrain is more rugged, with ancient, heavily cratered highlands rather than flat volcanic plains. The permanently shadowed craters have been cold traps for billions of years. And the specific rock types exposed at the South Pole may include material excavated from deep within the lunar crust by the large impact events that formed the South Pole Aitken Basin, the largest known impact crater in the past. Solar system, with a diameter of about 2,500 kilometers and a depth of up to 8 kilometers. Some of the South Pole Aitken material may include rocks from the lunar mantle, which has never been directly sampled. The composition of the lunar mantle is a key constraint on models of lunar formation and the giant impact hypothesis. This is the kind of sampling that makes planetary scientists genuinely excited about Artemis IV, beyond the purely engineering and logistics story. The rocks that astronauts collect from the lunar South Pole may answer questions about planetary formation that cannot be answered by any other means currently available. They may also raise new questions, as lunar samples consistently have. Every time scientists analyze a new Apollo sample with a better analytical technique, they find something unexpected. The way the Moon's geology has been studied from orbit has also improved dramatically since the Apollo era. The Lunar Reconnaissance Orbiter, launched in 2009 and still operating, has mapped the entire Moon at a resolution of about 50 centimeters per pixel, better resolution than most commercially available satellite imagery of Earth. It has created detailed topographic maps using laser altimetry, measured surface temperatures in the permanently shadowed regions, confirming the extremely cold conditions that allow ice to persist, and characterize the distribution of hydrogen-bearing material at the poles using a neutron detector. The Lunar Sea Raider Observation and Sensing Satellite mission, also launched in 2009, crashed an impactor into a permanently shadowed South Pole crater and detected water in the debris plume, the first direct confirmation of polar water ice. These orbital datasets provide the foundation for mission planning, but they have limitations. A neutron detector can detect hydrogen from orbit, but cannot distinguish between water ice, hydroxyl groups chemically bound to minerals, and hydrogen gas. Surface measurements are essential to determine exactly what form the hydrogen is in and how accessible it is. Core samples drilled from the permanently shadowed crater floors would provide the most direct characterization of the ice, its depth profile, and its concentration. Getting astronauts to the crater floor to take those cores is the goal. The operational challenge of exploring the permanently shadowed regions deserves more detailed discussion than it sometimes receives. These regions are in complete darkness, continuously. The floor of a permanently shadowed crater has never seen direct sunlight since the crater formed possibly billions of years ago. There is no solar power available on the crater floor. Any equipment operating there must carry its own power source, which at the extreme cold temperatures creates engineering challenges for batteries and fuel cells. The terrain on the crater floor is unknown in detail because orbital cameras cannot see into complete darkness. Only radar instruments and thermal infrared sensors have provided any characterization, and at limited resolution. The plan for accessing the permanently shadowed regions involves astronauts operating from the illuminated crater rim and descending into the crater for specific sampling operations, with time limits imposed by the life support endurance of their suits. The Axiom Extravehicular Mobility Unit is specified to support at least 2 hours of operation in the cold, dark regions. An astronaut could descend into the crater on foot, or possibly using a small rover, collect samples from the surface and from shallow drill cores, and return to the illuminated area before suit consumables are depleted. The exact logistics of this will need to be worked out as the detailed mission planning for Artemis IV proceeds, informed by the test data from Artemis II and III. The geology of the crater rim itself also has scientific value. Where the permanently shadowed crater floor meets the illuminated slopes of the crater rim, there is a gradient from extreme cold to moderate temperatures. This transition zone may have a distinctive mineralogy related to the migration and sublimation of volatile materials. Frost that forms on the cold side of the boundary during lunar night may sublimate and migrate when the same material is exposed to sunlight during lunar day. Over geological time, these processes could create patterns of volatile enrichment and depletion that record the history of the crater's thermal environment. The moon has no atmosphere, but it has what scientists call an exosphere, an extremely thin envelope of molecules that occupy the space immediately above the surface without interacting with each other frequently enough to constitute a gas, in the usual sense. The lunar exosphere contains water molecules, hydroxyl radicals, helium, neon, argon, sodium, potassium, and other species, all present at concentrations that would be considered an extraordinarily good vacuum by engineering standards. These molecules come from a variety of sources: solar wind ions that have been implanted in the regolith and later released, impact vaporization of micrometeorites, outgassing from the interior, and potentially water ice that has sublimated from the polar regions. Measuring the composition and behavior of the lunar exosphere near the South Pole, particularly near the permanently shadowed craters, can provide indirect information about the ice deposits below. Water molecules that sublimate from exposed ice patches at the crater floors will enter the exosphere and can be detected by sensitive mass spectrometers. The flux of water molecules, combined with models of exospheric transport, can help constrain the total amount of ice present and the rate at which it is being lost to space. Duster's measurements of dust behavior also connect to the exosphere story. The charging of dust particles by solar wind and by photoelectron emission from sunlit surfaces creates a complex electrostatic environment near the surface. In some circumstances, submicron dust particles can be electrostatically levitated above the surface, creating a low-altitude dust cloud that has been observed from orbit. This levitated dust could potentially transport volatile material from illuminated areas towards shadowed areas, contributing to the accumulation of frost. Understanding whether this mechanism is significant requires direct measurement near the surface. The seismic data from the South Pole Seismic Station will complement the geochemical and environmental measurements with structural information about the subsurface. Moonquakes detected by the station can be analyzed to determine the seismic velocity structure, essentially, how fast seismic waves travel through different depths of the lunar interior. Seismic velocity is closely related to composition and physical state. Solid rock conducts seismic waves faster than loose regolith, and ice has a different seismic signature than dry rock. By building up a catalog of seismic events and analyzing the waveforms, scientists can gradually build a three-dimensional model of the subsurface beneath the South Pole, including potential identification of ice-rich layers. The Thumper device that astronauts will use to generate controlled seismic pulses works on a shorter range and higher resolution than natural moonquakes, allowing characterization of the top few tens of meters of the subsurface. Reflection seismology. Analyzing how seismic waves reflect off boundaries between different material layers is a well-established technique for characterizing subsurface structure on Earth, where it is widely used in oil and gas exploration and hydrological studies. Applying it to the lunar South Pole to search for ice-bearing layers is a direct application of techniques that geophysicists have used on Earth for decades, adapted for the lunar environment. One of the most important but least discussed aspects of the Artemis program is the question of how human physiology responds to the lunar environment during extended stays. The Apollo astronauts spent at most 3 days on the lunar surface during the final 3 Apollo missions, which included extended surface traverses and significant physical activity. The Artemis missions are intended to eventually support stays of weeks or months. Understanding what happens to the human body during that length of time in the lunar environment is essential for mission planning. The reduced gravity of the Moon, about 1/6 of Earth's surface gravity, affects almost every system in the human body. On Earth, the cardiovascular system is constantly working against gravity to return blood from the lower extremities to the heart. In reduced gravity, this workload decreases, and over time the cardiovascular system can deconditioning in ways that create risks when the person returns to higher gravity. The musculoskeletal system similarly adapts to the loading conditions of its environment, muscles, and bones that are not bearing normal gravitational loads gradually weaken. The fluid distribution in the body shifts, affecting the vestibular system responsible for balance and spatial orientation. On the International Space Station, where astronauts experience near weightlessness, these effects are well documented and managed through daily exercise protocols using specialized equipment. On the Moon, the partial gravity environment is expected to produce smaller deconditioning effects than full weightlessness. But the effects are not zero and have not been directly measured for stays of more than a few days. The Apollo astronauts were on the surface too briefly to accumulate significant cardiovascular or musculoskeletal deconditioning. Extended Artemis stays will provide the first real data on these effects in the lunar gravity environment. The lunar dust inhalation risk is also poorly quantified. During the Apollo missions, astronauts brought substantial amounts of lunar dust into the lunar module on their suits, where it became airborne and was inhaled. Several Apollo astronauts reported upper respiratory irritation after their surface excursions, which they attributed to the dust. The chemical composition of lunar regolith includes silicates with sharp angular geometries, and some Apollo samples have shown a composition that, by analogy with Earth minerals, would be expected to cause lung damage at sufficient exposure levels. What constitutes sufficient exposure in the lunar context, and how effectively the improved dust mitigation features of the AxiomU suit will reduce exposure, are questions that will begin to be answered during Artemis IV surface operations. Radiation exposure during the surface stay is also a major health consideration. The lunar surface at the South Pole receives both galactic cosmic rays and solar energetic particles. The regolith provides some shielding. A person on the surface is shielded from below by about 3 meters of rock, but from above and the sides, the exposure is essentially the same as in deep space. Solar particle events, which can deliver a large radiation dose in a short time, are the primary acute risk. Galactic cosmic rays, which are impossible to avoid and penetrate most practical shielding materials, accumulate over time and increase the long-term cancer risk. The placement of the habitat in a location where natural regolith can be piled over it for shielding is one of the standard approaches discussed in lunar base design. The ice itself, if present in sufficient quantities, could serve as shielding material. Water is a good radiation shield because of its high hydrogen content, and hydrogen is particularly effective at stopping the secondary particles produced when galactic cosmic rays interact with other materials. The combination of radiation shielding and proximity to a resource for propellant production makes ice-rich locations doubly attractive for base siting. All of these scientific and engineering considerations, the ice chemistry, the geological sampling, the seismic monitoring, the dust characterization, the radiation environment, the subsurface structure, feed into a coherent picture of what the Artemis program is actually attempting to build knowledge about. It is not primarily a program about going somewhere. It is a program about learning enough about the Moon to make living and working there possible on a sustained basis. This is why the pace matters. Each mission builds on the previous one. The data from the Artemis II life support verification informs the design of the habitat systems for the surface base. The seismic data from early deployments informs subsurface structure models that guide where future drilling operations should be located. The dust behavior data informs materials choices for the next generation of suits and equipment. The ice composition measurements inform decisions about the design and siting of in-situ resource utilization facilities. The program is cumulative, and its value compounds over time. The institutional question of whether NASA and its partners can maintain the continuity and commitment required for this compounding to actually occur is perhaps the single most important non-technical variable in the equation. The history of the post-Apollo era includes multiple ambitious programs that were initiated, partially funded, and then canceled before they could deliver their designed capabilities. The Space Exploration Initiative of 1989, the X-33 Reusable Launch Vehicle Program, the Constellation program that Artemis partially replaced. Each cancellation represented a loss of investment, a dispersal of workforce, and a delay of the next attempt that ultimately cost more than sustaining the canceled program would have. The current political environment for Artemis includes both supportive and challenging elements. The program has bipartisan political support in the United States, partly because the economic benefits of aerospace contracts are distributed across multiple states and congressional districts. The geopolitical competition with China provides a strategic rationale that transcends partisan politics. But budget pressures are real, and the program's costs, particularly the SLS costs, are a recurring subject of criticism from policy analysts who argue that the money would produce more capability if spent on commercial alternatives. The decision to move toward the Centaur 5 upper stage and the standardized SLS configuration represents a partial response to these criticisms, reducing the ongoing development cost of the upper stage while maintaining the process government's core deep space transportation capability. Whether this approach produces the cost trajectory and launch cadence that would make the program financially sustainable in the long run remains to be demonstrated over the coming decade. What is clear is that the scientific and strategic case for a sustained presence at the lunar South Pole is strong. The ice is there, or the evidence strongly suggests it is. The geological record preserved in the polar highlands and crater floors is unique. The strategic value of being first to develop the infrastructure for in-situ resource utilization is real. The long-term economic potential of a permanently inhabited lunar base as a staging point for deeper solar system exploration is substantial. The foundation for getting there is being built, imperfectly and with delays, but being built nonetheless. As the Artemis II crew prepares for their flight, and as engineers continue to verify the systems that must work perfectly to bring them home safely, the broader story continues to unfold. The Chinese program is advancing. The commercial lander companies are developing their hardware. The international partnerships are forming and reforming. The permanently shadowed craters of the moon continue to preserve their ancient ice in the silent cold, patient in the way that geological timescales are patient, indifferent to the political and technological urgency of the small, warm creatures on the nearby blue planet who are finally, after a long pause, starting to make their way back. The next chapter of that story begins when the SLS engines ignite and a new generation of explorers climbs through the sky toward a destination that humans visited once and then walked away from 50 years ago. Whether the timeline holds, whether the technology performs as designed, whether the institutional commitment endures, these are the open questions. The science waiting to be done at the South Pole does not care about the answers to those questions. It has been waiting for billions of years. It can wait a little longer. There is a specific place on the moon that has captured the attention of planetary scientists and mission planners more than any other single location. It sits almost exactly at the South Pole, and its name is Shackleton Crater, named for the Antarctic explorer, Ernest Shackleton. Shackleton was famous for his ability to survive extreme conditions through ingenuity and endurance, a fitting namesake for a location that may determine the viability of human survival in one of the harshest environments in the place. Solar System. Shackleton Crater is 21 kilometers in diameter and 4 kilometers deep. Its floor has been in complete darkness for essentially its entire existence, billions of years. The walls of the crater are steep, in some places exceeding a 30-degree slope, which creates the effective cold trap that prevents volatile materials from escaping. The rim of the crater, by contrast, sits high enough that it receives near-continuous sunlight more than 80% of each lunar day, which is approximately 29.5 Earth days in duration. This unusual geometry makes the rim of Shackleton one of the best characterized natural solar power sites identified anywhere in the solar system outside of Earth. The Lunar Reconnaissance Orbiter has measured the surface temperature of Shackleton's floor at approximately negative 185 degrees Celsius on average, with some of the coldest spots approaching negative 240 degrees Celsius. These are the coldest surface temperatures measured anywhere in the inner solar system by orbiting spacecraft. At these temperatures, water ice is stable against sublimation over geological timescales. A molecule of water frozen on the crater floor will remain there for billions of years unless disturbed by an impact event or physical excavation. Scientists have detected elevated hydrogen concentrations on the crater floor through orbital neutron spectroscopy, consistent with the presence of hydrogen-bearing material such as water ice or hydroxyl compounds. Radar measurements from the Mini-RF instrument on Lunar Reconnaissance Orbiter have shown elevated circular polarization ratios in parts of Shackleton's floor, a signature that, when seen in radar data from Earth's own permanently shadowed polar craters, correlates with the presence of ice. No single orbital measurement definitively proves ice, but the combination of multiple independent lines of evidence pointing in the same direction makes a strong scientific case. Interestingly, recent analysis of Lunar Reconnaissance Orbiter data has also revealed that the illuminated walls of Shackleton Crater contain patches of ice exposed at the surface frost that is stable even in partially illuminated conditions because the temperature at those locations stays cold enough. For much of the lunar day, these wall deposits may be more accessible than the floor ice, as they do not require operating in complete darkness. But they may also represent a thinner, more recently formed layer of frost, rather than the ancient, deeply buried ice that scientists believe may exist on the crater floor. The discovery of surface ice on crater walls was published in 2019 and represented an important step in understanding the polar ice system. It suggests that ice is not simply confined to the coldest, permanently shadowed interiors, but exists in a continuum of exposures across the polar region. From deep, permanently shadowed craters, to partially shadowed slopes, to fully illuminated surfaces where ice is transient and exists only during cold parts of the lunar day. This gradient of ice stability is scientifically interesting because it preserves a record of how volatile materials migrate across the lunar surface over time. About 10 kilometers from Shackleton, in the broader South Pole region, lies a feature called the Haworth-Malapert Ridge, a complex of elevated terrain that sits in near-continuous sunlight. Plans for the Artemis South Pole base envision a surface habitat sited on this illuminated ridge, with relatively easy access to the adjacent shadowed craters for resource extraction and scientific sampling, while also having reliable solar power and favorable communication geometry with Earth. The specific location of the first crewed landing within this region will be determined by detailed analysis of the robotic precursor data, the surface hazard characterization from orbital cameras, and the operational logistics of the chosen landing system. The terrain of the South Pole presents navigation challenges that did not exist for the Apollo missions. The Apollo landing sites in the equatorial regions were selected partly for their relative flatness, which simplified the landing maneuver. The South Pole terrain includes slopes, boulder fields, and crater rims that create a more complex landing environment. The SpaceX Starship human landing system, which is approximately 50 meters tall at the landing configuration, must find a flat enough site within the target zone to land safely, a requirement that places tight constraints on terrain selection and navigation accuracy. This is one of the reasons that robotic precursor missions to the South Pole, including the Volatiles Investigating Polar Exploration Rover, known as Viper, a NASA robotic rover that was planned for deployment to the South Pole, but faced mission changes, are so important. Direct ground truth characterization of the landing site terrain, at a scale finer than what orbital cameras can provide, is essential for safe landing planning. The navigation systems of any lunar lander must be designed to handle the terrain they will actually encounter, not a simplified or idealized version of it. The thermal environment of the South Pole also creates engineering challenges that were not factors in the equatorial Apollo missions. The long lunar day and night cycle, 2 weeks of continuous sunlight, followed by 2 weeks of continuous darkness, creates extreme thermal cycles for equipment on the surface. Equipment that is designed to operate from a solar power supply must either carry sufficient energy storage to survive 2 weeks of darkness, or be designed to be powered down and restarted. Batteries capable of storing 2 weeks of energy at the power levels required by a surface base would be prohibitively heavy. Fuel cells, which generate power from stored hydrogen and oxygen, are an alternative, but require cryogenic storage of the propellants. Nuclear power sources, specifically small fission reactors, are being developed for this application, as they provide continuous power regardless of the day-night cycle. NASA and the Department of Energy have been jointly developing a fission surface power system intended for lunar and eventually Martian surface use. The system is designed to produce at least 10 kilowatts of electrical power continuously, which is enough to support a small habitat and basic operations. Multiple units could be deployed together to provide more power as operations scale up. The nuclear fuel is enriched uranium, and the system must be designed so that the reactor can be landed safely, started up remotely before crewed arrival, and operated without direct astronaut intervention for years. The development of surface power systems represents another of the enabling technologies that must mature alongside the rocket, spacecraft, and suit technologies if a sustainable lunar presence is to be achieved. Power is the master resource. Everything else on the surface, from life support to communications to propellant production to scientific instruments, requires electrical power to operate. Ensuring reliable, sufficient power is the first prerequisite for everything else. Water electrolysis for propellant production requires substantial power. Breaking water into hydrogen and oxygen requires about 15 watt-hours of energy per gram of water. Producing a kilogram of water-derived propellant, hydrogen, and oxygen in the ratio needed for rocket fuel requires roughly several kilowatt-hours of electrical energy. Producing the quantities of propellant needed to refuel a lunar lander would require sustained electrical power over extended periods. This power budget is one of the key constraints on the scale of in-situ resource utilization operations, and it reinforces the need for robust surface power systems. The propellant production process also requires handling and storing hydrogen and oxygen at cryogenic temperatures on the lunar surface, which involves its own set of engineering challenges. Cryogenic storage is more difficult on the Moon than on Earth, because the low thermal conductivity of vacuum means that the primary mode of heat transfer into a cryogenic storage vessel is radiation rather than convection, or conduction. Radiation-based heat transfer can be managed with appropriate insulation and surface treatments, but it cannot be eliminated entirely. Over time, heat leakage will cause boil-off, the conversion of liquid cryogen to gas that must be managed either by venting, which wastes propellant, or by active refrigeration, which requires power. Designing cryogenic storage systems that minimize boil-off losses over the months-long timescales required for propellant production and depot operations is an active engineering challenge. The question of where to store produced propellant also involves considerations beyond engineering. A propellant depot on the lunar surface represents a substantial capital investment and a strategic asset. Protecting it from accidental damage during landing operations, maintaining it during periods when no crew is present, and ensuring its availability when a mission arrives, requiring refueling, are all operational challenges that must be addressed. The answers will shape the architecture of the lunar economy that Artemis is intended to initiate. Beyond the immediate scientific and resource extraction objectives of the South Pole missions, the Artemis program exists within the larger context of humanity's eventual expansion to Mars. The Moon is not the final destination. It is the nearest, most accessible proving ground for the technologies and operational concepts that will eventually be needed to live and work on Mars. Many of the challenges are similar: reduced gravity, extreme temperatures, radiation exposure, the need for in-situ resource utilization, the requirement for closed-loop life support systems, the logistics of operating far from Earth without the possibility of rapid resupply. Mars has its own water ice, distributed at the poles and potentially in the subsurface at mid-latitudes. Mars has a thin atmosphere of carbon dioxide that could theoretically serve as a feedstock for producing methane and oxygen propellant, a process called the Sabatier reaction combined with electrolysis. Mars has day-night cycles and seasonal variations that create energy management challenges, similar in principle to those on the Moon, though different in detail. A sustainable human presence on Mars will require all of the same categories of capability, power, life support, propellant production, radiation protection, surface mobility that a sustainable lunar presence requires, but at a greater distance and with longer resupply delays. The value of using the Moon as a testbed for Mars mission concepts is therefore not just a rhetorical justification for the Artemis program. It is a practical engineering strategy. Every technology that is developed, tested, and operationally validated at the Moon can be adapted for Mars with greater confidence than if it were attempted at Mars for the first time. The dust behavior at the South Pole will be different from Martian dust in specific ways, but the general problem of managing abrasive airborne particles that infiltrate equipment is the same. The ice extraction and processing technology developed for the Moon will require modification for Mars, but the fundamental process engineering challenges are similar. The radiation environments are different in detail, but similar in category. The timeline for human missions to Mars extends well beyond the current Artemis roadmap. Current NASA planning discussions mention the late 2030s or early 2040s as a target timeframe, contingent on sustained investment and the continued development of the enabling technologies. SpaceX has publicly stated far more aggressive Mars ambitions, with founder Elon Musk discussing the possibility of a crewed Mars mission in the late 2020s. But most independent analysts regard this timeline as extremely optimistic, given the current state of development of the required systems. What is clear is that the path to Mars runs through the Moon. Not necessarily, because lunar propellant production is essential for every conceivable Mars architecture. Some mission designs propose going directly from Earth orbit to Mars, without a lunar stopover, but because the operational experience, the technology validation, and the institutional knowledge developed during the Artemis program provide a foundation that would be foolish to bypass. The cost of learning by doing at Mars, where communication delays prevent real-time ground support, where emergency return to Earth takes months rather than days, and where every failed component has a higher consequence, is vastly higher than learning at the Moon. In this sense, the delays and technical challenges of Artemis, frustrating as they are in the moment, may be understood differently in retrospect. A program that proceeds too quickly, that takes shortcuts under schedule pressure, that accepts unquantified risks in the name of meeting political deadlines, is a program that is likely to experience a catastrophic failure eventually. The Challenger and Columbia disasters during the Space Shuttle program demonstrated what happens when schedule pressure overcomes engineering caution. Not just the loss of missions and crew, but multi-year program pauses that ultimately delayed progress more than a slower, more careful approach would have. The current Artemis program, with its redesigned missions and standardized hardware and reduced risk appetite, reflects a philosophy that is different from Apollo's sprint mentality. It is attempting to build a program that is durable, that can survive technical setbacks, budget pressures, and changes in political administration without losing its fundamental direction. Whether it succeeds in this is a question that will be answered over years and decades, not in a single launch. For now, the 4 astronauts in quarantine in Florida represent the near term of that question. They have trained for years for a 10-day mission that will carry them farther from Earth than any human being has traveled in half a century. The rocket that will carry them has been repaired and tested and returned to the pad. The systems that will keep them alive have been checked and rechecked. The plan for how they will return to Earth has been revised to give them the best chance of surviving the heat of re-entry. If the launch holds, the world will watch a human crew leave Earth orbit for the first time since the Apollo era. The sight of the SLS rising from Pad 39B and arcing out over the Atlantic will be a moment that connects the present to a past that many thought might never be repeated. And it will also be the first step toward a future that the Apollo program never attempted to build. A sustained, expanding human presence in the solar system that begins at the Moon and extends in time to Mars and beyond. The science is compelling. The strategic necessity is real. The technology is advancing. The commitment, imperfect and contested as it always is in large public programs, is present. The rocket is on the pad. The next chapter is about to begin. The story of how we return to the Moon is also, in an important sense, a story about what kind of species we are. It is a story about our relationship with the limits of our environment, our drive to extend the boundaries of where we can live, and our willingness to invest in futures that we will not personally inhabit. The first astronauts to walk on the south pole of the Moon, assuming the current plan holds and the technology cooperates, will be doing something that no human being has ever done. They will be in a place where no human has ever stood, collecting materials that no laboratory on Earth has ever analyzed, making observations that no instrument has previously made. The experience of being on the lunar South Pole, in the low sun that grazes the horizon at a constant shallow angle, standing on the rim of a crater whose floor has been in darkness since before multicellular life evolved on Earth, that experience will be unique in human history. And it will also be the beginning of something. The first base camp at the South Pole will not be the last. The first propellant produced from lunar ice will not be the last. The first human step into the permanently shadowed region will not be the last. Every large-scale human endeavor that we now take for granted began with a first step that was technically difficult, expensive, politically contentious, and uncertain in outcome. The first transatlantic telegraph cable, the first transcontinental railroad, the first commercial aviation route. All of these were accomplished at enormous cost, and with considerable doubt about whether they would succeed. And all of them eventually became so ordinary that the difficulty of the initial achievement is almost forgotten. The first permanent human settlement on the Moon, if it occurs, will eventually be in that category, remarkable in retrospect, ordinary in the future that it enables. Getting there from here requires the rocket on the launch pad in Florida to lift off successfully. It requires 4 astronauts to make it around the moon and home safely. It requires all of the subsequent missions to proceed without catastrophic failure. It requires the political and institutional commitment to persist across changes of administration and periods of budget pressure. It requires the commercial technology development, SpaceX's Starship, Blue Origin's Blue Moon, the Centaur 5 integration, the fission surface power system to succeed on a schedule compatible with the mission timeline. None of these requirements are guaranteed. All of them are being worked on simultaneously by thousands of engineers and scientists at NASA, at its international partners, and at commercial companies. The probability of the full plan proceeding exactly as currently described is not high. Plans in space exploration almost never execute exactly as written. Apollo certainly did not. The program lost 3 astronauts in a ground test fire, had a near-fatal explosion on the way to the moon during Apollo 13, and made multiple mission replanning decisions along the way. What the Apollo program demonstrated is that a committed program with skilled people and sufficient resources can absorb setbacks and continue toward its goal, and that the goal, if worth pursuing, is worth the setbacks. The Artemis program has already absorbed substantial setbacks: budget overruns, schedule slips, mission redesigns, heat shield anomalies, hydrogen leaks, helium valve failures, and the rolling back of a 98-meter-tall rocket in the middle of the night to fix a part that was inaccessible from the pad. And it is still going. The rocket is still on the pad. The crew is still in quarantine. The launch is still on the schedule. The program, for all its imperfections, has not been canceled. That is itself a kind of evidence. In a political environment where large government programs are routinely canceled when they encounter difficulty, the persistence of Artemis, now approaching a decade since its initial announcement, having survived multiple presidential administration changes, multiple budget battles, and multiple technical crises, suggests that the underlying rationale for the program is strong enough to keep it alive even when the going is difficult. Whether that persistence continues through the lunar landing and beyond remains to be seen. What is known is that the moon is there, that the ice is there, that the science is there, and that the first step back toward it is about to be attempted. 4 human beings are about to do something that no human being has done in more than 50 years. And if they succeed, the 50-year pause in human deep space exploration will be over. The Orion capsule sitting atop the SLS rocket on Pad 39B is not the same as the command modules that carried the Apollo crews. It is larger, more capable, equipped with more advanced avionics and life support systems, and designed to be reusable in ways that the Apollo capsules were not. The SLS rocket is not the same as the Saturn V. It uses different engines, different materials, different software, and a different launch profile. The crew is different, more diverse, more recently trained, carrying the knowledge of 50 years of human spaceflight experience that the Apollo crews did not have. But the destination is the same, the moon. And beyond the lunar flyby of Artemis II, the destination after that is the same too. The south pole of the moon, with its ancient shadows and its ancient ice, is the same as it was when Eugene Cernan scratched his initials in the dust 900 kilometers away and climbed back into his spacecraft. It will be the same when the first Artemis astronaut descends into Shackleton Crater with a sample collection bag and a drill. Some things in the solar system operate on timescales that dwarf human history. The ice in the permanently shadowed craters has been accumulating since before the dinosaurs existed. It will still be there after everything we build on the lunar surface has been worn down by micrometeorites and solar radiation. The geological record in the lunar highlands has been waiting to be read for 4 billion years. It can be patient for a few more years while we fix our hydrogen valves and repressurize our helium lines. The science, the strategy, and the ambition are all in place. The next step belongs to the rocket. And after the rocket, to the 4 human beings who will ride it toward the moon, trusting the engineers who fixed the seals, and the scientists who revised the re-entry trajectory, and the thousands of people who have spent years preparing for this flight. If everything works as intended, their journey will mark the end of the longest pause in human exploration since before the age of sail. And it will be, in the long story of our species reaching outward from the world where we evolved, just the beginning. One of the most underappreciated aspects of returning to the moon after such a long absence is what that absence itself represents. The 50-year gap between Apollo 17 and the Artemis missions was not caused by any single decision or failure. It was the product of a sequence of events that collectively redirected human spaceflight inward toward low Earth orbit. toward the Space Shuttle program, toward the International Space Station, and away from the deep space destination that the Apollo program had demonstrated was reachable. The Space Shuttle program, which flew from April 1981 to July 2011, was in many ways a remarkable achievement. Over the course of 135 missions, the shuttle flew more than 800 individual crew members, deployed and repaired the Hubble Space Telescope, assembled the International Space Station, and demonstrated the operational feasibility of a reusable crewed spacecraft. But the shuttle's design required it to remain in low Earth orbit. Its maximum altitude capability, around 600 kilometers in specialized configurations, was nowhere near the 390,000 kilometers required to reach the Moon. The shuttle was a profoundly capable Earth orbit vehicle that could not, by design, take humans to deep space. The decision to build a shuttle, rather than a next-generation deep space capability, was made in the early 1970s under the Nixon administration, when the political will to fund another moon program had evaporated. The shuttle was justified partly on economic grounds that claimed that a reusable spacecraft would reduce the per-flight cost of access to orbit, and partly on the premise that a permanent, flexible presence in low Earth orbit was the next logical step after Apollo. Both justifications proved to be partially correct and partially wrong, in ways that took decades to fully understand. The shuttle never achieved the cost reductions its advocates projected. Its operational costs were higher than anticipated, and its reusability was more complex and expensive to maintain than the original design suggested. The two catastrophic accidents, Challenger in January 1986 and Columbia in February 2003, each resulted in the loss of 7 crew members and multi-year pauses in the program. When Columbia disintegrated on re-entry over the southern United States, pieces of the orbiter were found scattered across parts of Texas and Louisiana. The subsequent investigation produced a famous conclusion. The physical cause of the accident was a piece of foam insulation that had struck the leading edge of the left wing during launch, creating a hole that allowed superheated atmospheric gases to enter the wing structure during re-entry. But the deeper cause was identified as an organizational culture that had normalized the risks associated with foam debris strikes and failed to respond appropriately when engineers raised concerns about the damage. This organizational lesson, the technical risk, is shaped not just by the hardware, but by the culture and processes of the people who operate it, has been deeply influential in the way NASA approaches risk management in the post-shuttle era. The independent safety boards and review panels that have become a standard feature of human spaceflight programs, including Artemis, exist partly as a direct response to the Columbia accident. The independent safety review panel that warned about compounded technical risk in the original Artemis III landing plan is a direct institutional descendant of the Columbia Accident Investigation Board. After the shuttle program ended in 2011, the United States had no domestic capability to launch crew to the International Space Station. For nearly a decade, American astronauts rode Russian Soyuz spacecraft to reach the station, paying the Russian Space Agency tens of millions of dollars per seat. This situation was deeply uncomfortable politically, and the development of commercial crew transportation by SpaceX and Boeing was partly motivated by the desire to restore American independent access to low Earth orbit. SpaceX's Dragon capsule, flying on the Falcon 9 rocket, began carrying NASA crew to the station in November 2020, ending the dependence on Russian transportation. Boeing's Starliner capsule had a more troubled development, but eventually carried its first crew mission in 2024, though with technical problems related to the spacecraft's thruster and helium systems that resulted in a prolonged stay at the station. The fact that 2 independent American commercial crew systems now exist, even if both have faced technical challenges, represents a genuine diversification of American crewed spaceflight capability. The development of commercial crew capability provides important context for understanding the Artemis program. The lesson of commercial crew is that competitive market dynamics, combined with NASA oversight and certification requirements, can produce capable human spaceflight systems at lower cost than traditional government development contracts. SpaceX developed the Dragon crew capsule from a commercial cargo version in roughly 4 years, at a cost to NASA of approximately $400 million, a fraction of what the government-contracted Orion capsule has cost. This comparison is not entirely fair, because the Orion is designed for deep space missions with radiation shielding and heat shield requirements that Dragon does not meet, but the cost differential is large enough to be meaningful. The extension of commercial development principles to the Human Landing System, SpaceX's Starship, and Blue Origin's Blue Moon is an attempt to apply the same cost reduction logic to the lunar surface access. Problem? Whether this will work at the scale and complexity required for lunar surface operations is an open empirical question. The surface of the moon is much more technically demanding than low Earth orbit, and the human landing system must perform its critical functions docking with Orion in lunar orbit, descending to the surface, ascending back to orbit, with no immediate rescue option available if something goes wrong. The integration of government deep space transportation hardware with commercial surface access systems creates a mission architecture that is more complex to manage than either a fully government or fully commercial system would be. NASA must verify and certify the commercial systems while also integrating them with the government systems in ways that the commercial providers are not required by their contracts to accommodate. The boundaries of responsibility, liability, and decision-making authority between NASA and its commercial partners are being defined in real time through the process of developing and testing the actual hardware. This is new territory for human spaceflight, and the way it is navigated will establish precedents that shape the industry for decades. If the hybrid approach succeeds, if the commercial landing systems meet their performance requirements, if the integration with government hardware works smoothly, and if the cost of surface access is substantially lower than it would have been under a traditional government contracting model, then the template for future programs involving both government and commercial elements will be established. If it fails, or if the cost savings do not materialize, the debate about the appropriate role of commercial providers in human deep space exploration will continue. From the perspective of the science, the organizational questions are secondary. What matters for the scientific objectives of the mission is that functional hardware reaches the South Pole, that the instrument's work is designed, that the samples are collected and returned to Earth without contamination, and that the data is shared with the scientific community for analysis. How those outcomes are achieved through government hardware, commercial hardware, or some combination matters less than whether they are achieved. The scientific community has been waiting for South Pole samples and in-situ measurements for a long time. Every planetary science decadal survey for the past several decades has identified lunar South Pole samples as a high priority objective. The permanently shadowed regions are unique in the inner solar system, as cold traps that have preserved material from the early bombardment period essentially unchanged. The ice, if it can be recovered and analyzed, represents a time capsule from the first billion years of the solar system's history. The practical process of getting those samples from the moon to Earth and distributing them to laboratories for analysis is itself a complex logistics challenge. The Apollo samples were handled under strict curation protocols to prevent contamination and preserve their scientific integrity. The same protocols would need to be applied to Artemis samples, but the samples from the permanently shadowed regions present additional challenges. The ice, if present, must be maintained at cryogenic temperatures throughout the return journey and on Earth to prevent sublimation. Sample containers capable of keeping ice at near absolute zero temperatures through re-entry and recovery are not standard equipment. The development of such containers is another of the enabling technologies required before the full scientific potential of the South Pole ice samples can be realized. All of this, the cryogenic sample containers, the seismic stations, the dust sensors, the spacesuits, the lander, the rocket, the capsule, the heat shield is part of a single integrated system that must work together. The weakest link in any part of the chain determines the overall success or failure of the mission. This is why the engineers checking seals on the interim cryogenic propulsion stage in the middle of the night are just as important to the eventual South Pole science as the planetary scientists designing the sample collection. Protocols. Every person working on every part of the system is contributing to the same outcome. And that outcome, if it is achieved, will be the beginning of an era that scientists have anticipated for decades. The ice of Shackleton Crater, analyzed in laboratories around the world, will tell a story about the early solar system that no other sample can tell. The seismic data from the South Pole will reveal the interior structure of a world that has been geologically frozen for 3 billion years. The geological samples from the ancient highlands will extend the chronology of the lunar surface back to the formation of the solar system. And the engineering data from the in-situ resource utilization demonstration will determine whether the next phase of human exploration, extending beyond the moon toward Mars, is economically feasible in the coming decades. This is what is actually at stake when the Artemis II crew climbs into the Orion capsule and the SLS engines ignite. Not just the spectacle of a rocket launch, though that spectacle is real and worth appreciating, Not just the symbolism of humans returning to deep space, though that symbolism matters. What is at stake is the decision, made through action rather than through words, about whether humanity is going to be a multi-world species or whether we are going to remain, by choice or by default, permanently resident on the single planet where we evolved. Every civilization in history has eventually pushed to the edge of its known world. Sometimes the push succeeded and sometimes it failed. But the drive to go beyond the known boundary is one of the most consistent features of human cultures across time and geography. The edge of our known world right now is low Earth orbit. Everything beyond it is territory that we have visited briefly and then departed. The Artemis program is an attempt to change that, to extend the permanent range of human presence to include another world for the first time. It is an attempt that has been delayed. It has been complicated. It has been more expensive than planned and slower than hoped. It will probably be delayed further before it succeeds. But it is continuing, and the rocket is on the pad. The 4 crew members of Artemis II, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, each bring different backgrounds and perspectives to what will be a historic mission. Wiseman, a former Navy test pilot and NASA astronaut who has previously served on the International Space Station, will command the mission. Glover, also a former Navy test pilot and astronaut, will serve as pilot, and if the mission proceeds as planned, he will be the first African American to travel to deep space. Koch, a research engineer and astronaut, will be the mission specialist whose previous spaceflight included the record-setting long-duration stay on the International Space Station. Hansen, a Canadian Space Agency astronaut and former Royal Canadian Air Force fighter pilot, will be the 4th crew member and the first Canadian to travel to deep space. Their collective experience represents the kind of cross-disciplinary background that complex exploration missions require. Test pilots bring structured thinking about system failures and emergency procedures. Research scientists bring the analytical skills needed to evaluate scientific results in real time. The international composition of the crew reflects the Artemis program's commitment to collaborative exploration. Together, they will face conditions that no human crew has encountered in more than 50 years, and they will do so with systems that are flying crewed for the first time. That combination, experienced crew and first flight hardware, is the fundamental tension at the heart of every early crewed mission. There is no substitute for operational experience, but operational experience can only be gained by flying. The solution is to be as systematic as possible in preparing for contingencies, to test everything that can be tested before the flight, and to accept that some level of unknown risk is unavoidable when doing something genuinely new. The Artemis program has done its testing. The hardware has been repaired and verified. The trajectory and re-entry plan have been revised based on what was learned from Artemis I. The crew is ready. Now it is time to fly.